All right, everybody, ladies and gentlemen, I want to thank you for coming to our session. And as you can see from the screen, this is on full text search, rapidly finding the needle in the haystack. And today we're going to learn a little bit more about how our full text search can take advantage of the performance and scalability that we have in Couchbase Server as well as in mobile. And to do that, we have Marty Schoch, who's going to lead the demonstration and conversation anyway, and get us started. So Marty, it's up to you.
Thank you. As you just heard, my name is Marty Schoch, and we're going to talk about full text search today. You've probably already heard a lot about the Couchbase Data Platform. This is something I'm very familiar with. I've been with Couchbase for over 6 years now. And the interesting thing is, going all the way back 6 years, the principles have remained the same, right? At that time, key value was all we had, but it was the memory-first architecture you're familiar with. And what we've done over the coming years is we've added services around it, right? These are adding additional capabilities, but not taking away what you always had with the key value access. It's kind of the core philosophy of Couchbase is you can kind of pick and choose the services you need. If you need indexing and query, you add that service. If you need full text, you add that service. Because each of these things come with some costs, some additional resources, and so you want to be able to pick and choose what you need. Taking it further, we have what we call multidimensional scaling. And that's the idea that you can not just choose to run these services or not, you can actually scale them independently. If you have a really heavy indexing and query workload, you can devote a number of servers to that. You can scale down full text search or up, depending on your needs. So obviously in this talk, we're going to look a lot deeper at the full text search service, one of our most recent additions to the platform. Now, a common question we get is sort of, what's the difference between search and query? Like at that 1,000-foot level, they kind of look the same, right? You have this idea of, I'm going to tell you what I want, and you're going to give me documents back that match that criteria. So at that level, there is overlap. And these are really, I think of these as guidelines or sort of steering you in the right direction, because these two features do have some overlap. You may not always have a clear choice of one or the other. There's going to be situations where you can do it with either. So let's go through these. The first is that search can match across multiple fields. What we mean here is, let's say you have a schema, you have like a name field and description field, someone types in some text to search. You want to be able to find a match in either of those fields. And even better, they may not even know your schema, right? The user running the search may not know whether you have a name field or a description field or title, whatever. Now, that's not to say you couldn't do that with Nickel, right? In Nickel, it would just be on you to have indexes on all the appropriate fields and to write the additional clauses. So this is something that with full text, you get sort of for free. The second is that search supports inexact matching. What we mean here is actually two different kinds of things. The first is the ability to configure language-based stemming. So if you can tell us, look, this field is in English, we're going to be able to do additional transformations to make those matches in that field better. The other aspect of that is something we call fuzzy search. You want to be able to handle typos and spelling mistakes, both in the queries and in the documents, and still find matches. Again, that's not to say you couldn't do that with a Nickel query, but you would be writing that logic yourself in the query, and it would get very cumbersome. And the final point is that search results are ordered by relevance. So again, that's sort of by default. You can override the sort order just like you can with Nickel. But the key is that the relevance is a measure of how well a document matches your search. And that's something that, again, could you write a function in Nickel and sort of compute that? Yes, but that would be a lot of complexity and things you'd have to maintain yourself. And that's something we do for you with full text search. Now, the title of this talk was Rapidly Finding Needles. What does that mean? Well, in Couchbase, users typically have large sets of documents, right? It's not uncommon at all to have millions, tens of millions, hundreds of millions of documents in Couchbase. And so how do we find information in those big piles of data? Well, not surprisingly, we build an index, right? We organize the data so that we can go through it faster. And in full text, we built something called an inverted index. So let's look more specifically at Couchbase and how we build one of these indexes. This is the main dashboard. This is what hopefully many of you have seen working with Couchbase. And there is an entry on the left-hand side for search. And so to get started with search, that's what you're going to do. You're going to click into that. And this takes you to what I call like the full text homepage or the full text dashboard. What you see here is a table. It's empty right now, which is why it looks kind of confusing. But it's a table listing all the indexes we have, and we haven't built any yet. So it's empty. And we're going to go over to that Add Index button. And when we click that, it takes us to the Add Index form. Now, this form looks complicated, and it is. There's a lot going on here. But the good news, and what I want you to focus on right now, is we can actually ignore most of it to build our first index. So getting started with this is pretty easy. We actually only need to fill out two aspects of the form. The first is that we have to give the index a name. I'm just going to call it travel. And second, we have to choose which bucket we want to index. I've chosen the travel sample, which is one of the sample buckets we ship with Couchbase. Everything else we're going to skip over for now. We're going to do a live demo later, and we'll see a little bit more about some of the things we can configure later. But for now, we're just going to stick to the defaults and go down to that Create Index button. When we build that, it takes us back to this full text dashboard. And now that table that was empty before, we have that entry called travel. And we see building an index takes a little bit of time. So the progress is indicated there. It's just at 30%. That's going to eventually go up to 100 when it's complete. And one of the nice features of our service here is we can also run searches directly inside the admin UI. So what you see that little says search this index, we can actually just write our first query there. So this is the travel sample data set. So it has things like landmarks. And so I'm just going to search for the word water. We'd expect that's probably going to match. And so here we go. We got our first search result page. If we look a little closer, we see that returned 467 results. Now, just to give you a perspective, the travel sample data set has about 33,000 records. So that's a decent number of hits within that. It took 4 milliseconds on the processing on the server side. And now let's look at those results. As you see, it's only returning document IDs, and that might be a little surprising to you. This, again, goes back to some of the philosophy in Couchbase, right? We are attempting to not assume too much about what you want. So we actually build a very lean index by default. What you might have expected here would be to see some of the actual data, some highlighting, showing you like some of the snippets of why did this document match. And so we'll see later on in the demo how we can enable that capability. But we just don't include it by default because philosophically we don't want to assume too much. We want to build that lean index to get started. So with that, let's switch over and do a live demo. I'm going to try and make things a little bit bigger here. OK, so in this demo, what I'm going to try and do is illustrate those 3 principles I talked about earlier. If you remember, the first one was the ability to search and get matches across multiple fields. So let's go ahead and build an index. I'm going to build a custom index this time. I'm going to call this one travel custom. I'm going to select the travel sample bucket. Now, again, in that screenshots that we walked through before, we just didn't configure anything else. But we're going to actually customize this one. On this default type mapping, the first thing we want to do is we're going to take control of which fields get indexed. Right? By default, it indexed all the fields that it found. But we're going to edit this mapping and say only index specified fields. Let me try and make that one little size bigger just so everyone can see it. Only index specified fields. And what that means is if I don't tell it about any other fields, it won't index anything. So you'd actually get essentially an empty index if we just left it at this point. But we're now going to tell it about some fields. So I'm going to hit insert child field. And the first field I'm going to add is something called name. Actually, let me switch over just so you can see. This is what, a little too big. This is what one of the JSON documents look like. So we see it has a name field. And I think the other one we're going to index is the content field. So I'm configuring the name field. Now I'm going to check one other box. As I said earlier, we were only getting the document IDs in that first search. That's because the fields were not stored by default. So I'm going to check this box to store the field. And then I'm going to save that. I'm going to add one other field. This one's called content. And I'm also going to store that field as well. So again, just to recap, we're only going to index these 2 fields that I've specified. One is called name and one is called content. And we've enabled the storage of those fields. Now, just to keep things speedy, I'm going to also change the index type. Ignore that for now. At the end of the talk, we'll go deeper into that new storage type. And the UI isn't rendering particularly interestingly here with that zoomed in. So we're at 78%. So this index is still building. Let's go ahead and run a search. And I've, again, crafted some searches to sort of highlight the features we're going to look at. So I'm going to search for the word taco. And Let me make that bigger again. First thing we notice is that first hit, we see it had a match in the content field, and it also had a match in the name field. So again, this illustrates how search was able to recognize that multiple fields had a match in this case. But it also, again, it works in either case, right? Here's a document where it only matched the name field, and then here's another document where it only matched in the content field. So that's one of the power of FTS. The search, you notice I didn't have to specify any field name when I ran the search, and it automatically looked in those fields that we put in the index. It's pretty simple, but it's useful to illustrate that. So now let's go back to that second principle. The idea that when we do matching, we want to be able to have inexact matching as well. Let's see how we can tweak this index a little bit more for that purpose. So what we're going to do different this time is instead of creating a new index, I'm going to go back in and I'm going to edit the index. And if we scroll down, there's a section here called Advanced, and I'm going to expand that. And there's an option here called Default Analyzer. Now, when I had configured the content and the name field, I could have specifically chosen an analyzer for those fields, but I didn't choose one. So it's using this default analyzer that's configured at the bottom. And the default analyzer is something called Standard. Standard's an analyzer which doesn't make too many assumptions about the data, right? It tries to not assume what language it is, but it makes enough assumptions that we get some pretty decent behavior, and that's why it's the default. What we're going to do this time is we're going to switch that over to EN, which is the analyzer for English. So we're basically telling it the content in this is English. And by doing that, we're going to see some additional behaviors when we run searches. So that's the only change I'll make. I just changed that default analyzer, and I'm going to update. Now, it's important to note in full text, when you edit an index definition, it needs to rebuild the index. So you will notice that indexing progress is going to go down and come back up as it completes building the index. So let's try a search this time. I'm going to search for the word surfing. And the first hits you see here, they contain sort of exact matches for the term we search for, right? So that's not interesting. That would have worked just like last time. But if we scroll down a little more, if we look at this hit number 3, we see, well, OK, that one would have matched before because surfing matched in the name field. But we notice these 2 hits in the content field are for the word surf. That would not have matched before. So while this document would have been a part of the result set, it's most likely scoring higher now because more of the content is matching. So this is an example of how changing the analyzer actually could have improved the quality of your search results, right? If we scroll down a little further, we see there are some documents, like this item number 6, that would not have even been in the result set at all because we would have just missed that document completely. So again, by configuring the English analyzer, we see how that affects some of the results we get. Now that was for choosing a language-based stemmer. There's another capability, which is the ability to do fuzzy searches. So let's imagine someone searches for the word burrito, but they spell it wrong and they put 3 R's, right? They're just being a little careless as they typed it. It doesn't match anything. Well, that makes sense, right? In the whole document, there's no one happened to misspell it that way. But what we can do is, with this syntax, I'm going to put a tilde1, which is a fuzziness with what we call edit distance of 1. And now when we run that search, we notice we do get those matches for burrito. But not just burrito, we're also getting matches for burritos, right? And you might think, well, that should be an edit distance of 2. But remember, we're still using that English-based stemmer. So burritos and burrito got stemmed down to the same term. And then burrito with 3 R's matched it within an edit distance of 1. So again, these are things, what I want to highlight there is not just that you have these 2, but they actually work together in terms of increasing the number of things that are going to match. Now again, you also want to keep in mind, matching more isn't always matching better. So you always have to be mindful when you're doing these things of reviewing the quality of the results you're getting, right? It's not an automatic thing that just doing more stemming and getting more matches gives you better results. Now that leads us to our third topic, which is the idea that our search results are ordered by a relevance score. So let's run a search. This is microbrewery and food. And I have to, before we go on, I should explain, make it bigger so people can see. I'm putting a plus before the microbrewery and a plus before food. That's, in this query syntax, it makes it sort of a must clause. And what it means is like, those terms have to be in the document. We'll see when you add other terms without that plus that it means they're sort of optional, and it's like they can help influence the score, but they're not required. And again, I've crafted this search on purpose to illustrate this point, right? The reason I chose this one was it gives us 2 documents, and only 2 documents. So we can sort of theorize and try and understand why is this document ranked higher or lower than the other one. So let's look at that, right? Both of these documents contain the word microbrewery, or again, something that had stemmed to microbrewery, and the word food. But one thing you might be puzzled by is food occurred twice in this second one, but it's actually scored lower. Anyone in the room have an idea why that might be? Not in this case. Those are both stemmed down to just microbrewery. So inside the index, they'll actually be the same term for both documents. It's not case. So again, the analyzers have made everything lowercase at this point, so it's not the case. But two good guesses. Anyone else? We'll take one more. Could you repeat that again? It's actually not related to the exact matches in this case. That's okay. I appreciate the input. Thanks. We have to keep moving. I'm going to give you the answer. What's happening here is the other thing to keep in mind is the length of the field matters. So again, if you think about it, food, even though it only occurred once, it's actually 25% of the whole content of the field, right? So that deems it more significant overall in the document. Whereas in the second one, food occurs twice, but it's probably at least 20 words, so it's around 10% of the overall content of the field. So again, I just wanted to illustrate that that's a factor in terms of how these things score. Sometimes it's not obvious, and you do need to kind of get into a little bit about how the scoring works. Because ultimately what happens, end users come to you and say, I don't like the way the search results are ordered. Why is this one ranked higher than the other? And so when you use this service, you do have to kind of come to an understanding of how things are scored. So there's one other thing I wanted to play with, which was, what if we wanted to sort of force this order to get reversed? What could we do? And again, just to keep it, we're not set up for a very interactive environment here with the microphone, so I'm just going to go ahead and show you. What I'm going to try and do is I'm going to add the word trucks. Now, you notice trucks only occurs in the second document. So if I add trucks, now I'm not going to add it with a plus. I'm just going to leave it without the plus. And I could do truck or trucks. It actually doesn't matter. If I do trucks, now that one is ranked higher. And again, the reason to think about it is it's sort of like that satisfied all three of the things we're looking for, whereas the second one only satisfied two of the three. Now, if I had put the plus in front of trucks, exactly, the second one would not appear in the search results, right? Because that's not satisfying that requirement. So those are the three main principles we talked about. Again, searching across multiple fields, having the inexact matching, and then now coming to some understanding of how the relevance works in terms of ordering the search results. Now, what I wanted to do was a little more interesting, more advanced use case. So I have another data set. This data set is review data. So we can see a sample document here. Let me make that a little bigger. The only two fields we're really worried about is we have a text field and we have a date field. And the reason that's interesting is one of the most common questions I get from users is, look, I get the search results. They're good, but I get a bunch of old documents at the top. I'd really rather have some notion of freshness and have like newer documents be near the top. And a common thing you might think about is, well, maybe I would just sort the results by their date. But if you think about it, that doesn't really solve your problem, right? Now you're completely ignoring the relevance. You could have a document that just sort of barely matches the user search criteria, and it's at the top just because it's the newest. So what you really want is some sort of blending of the relevance and the recency of the document. So this is not a complete solution, but I just wanted to illustrate that it is possible to do that with the functionality we have. So let's take a closer look at this. And we do need to build an index for this. It's in a separate bucket. So I'm going to call this reviews. Similar to before, I'm going to scope it down just to certain fields. So I'm going to say only index specified fields. I'm going to add a child mapping. I think the field names are different here. I'll make sure I get it right. Yeah, so this has a field called text. And again, we'll store it so we can see why things are matching. And the second field, we're going to configure it a little differently. If you remember, the field is called date, but I'm going to also change that type. It defaulted to text, but I'm actually going to tell it that's a date, or date time is the name here. And I'll also store it just so we can see that in the results. And again, I'm going to use this newer version of the index, just so it's a little faster. And we'll get that started building. Now this index is 100,000 docs versus 30,000, so it takes a little longer. So while it's building, I just want to put that on pause for a second. We're going to jump over and look at some of the statistics. I just clicked on the bucket and then the statistics link. So this is right with all the other bucket statistics you're probably already familiar with. because we're creating an index on it, a new section shows up with the name of the index here. So I can actually expand that. And here we see some stats about the index while it's building. The document count is this first box. That's going up. Again, the index is building. There's another stat, sort of how many are left. That's going down. Records to persist. Again, like it's the key value, right? It's a memory-first architecture. So we index the content in memory first so that it becomes searchable as quickly as possible. But we're ultimately persisting at the disk, so it's durable as well. So this is a stat which can tell you sort of like how much is just sort of floating in RAM at the moment. And we have a stat for disk size as well. That's something we'll talk about a little more at the end of the talk. It will go up and down because there's sort of initial forms of the data, and then it gets compacted over time, and so the data size will fluctuate. It'll ultimately settle down. As you see, we got to all 100,000. So our index is ready. And actually, I just finish. The stats are organized. These left two columns are sort of relating to indexing, and the right two columns are related to searching. We haven't run any searches. That's why they're sort of all stuck at 0 right now. But let's go back and run a search. What I'm going to search for is, let's just do burrito. So again, a user is searching for burrito, and they get, let's remember this, 586 results. But if we look at it, this one's from 2015, this one's from 2011, 2014. So these are kind of older results. What could we do to sort of make fresher results appear near the top, but not change the result set and not change sort of the fact that we want good matches near the top as well? So what we're going to do is, the first thing I'm going to do is I'm going to put a plus in front of burrito. That's because even though I'm going to add more clauses, it has to have burrito in it still, right? So there's a bit of tweaking, and if you think about it, your application is going to be adding these kinds of things, right? This is taking the user's query, and now you're going to be transforming it to sort of run a slightly different query in the background. So this is an example where you have to be careful how you're tweaking what they provide you to make sure you're still matching their intent. So that's why I'm really doing this, right? The users wants to find documents containing a burrito, and I don't want to lose that property. So I'm going to prefix it with plus burrito, and I'm going to add an additional one. This one is scoped by a field, so I'm going to say date : greater than. And what I'm going to do is I'm actually just going to pick a date. Now this is arbitrary, right? I've just chosen the end of 2015, so it's December 31st, 2015. And then that little caret 10 means I want to boost that by 10. So the net result here is this doesn't have a plus, so it shouldn't change the result set at all. It's just saying the documents that are newer than, and that's why it's greater than, newer than the end of 2015, I want to influence their score by boosting it. And it's not as simple as just a multiplication, so you have to play with the numbers sometimes to get the effect you're looking for. But in this case, I've chosen 10 just as an arbitrary boost. And so let's run it and see what happens. So the first thing is we notice, okay, we accomplished that. We got the exact same result set. Or again, we've got the same number of results. We're assuming it's the same result set for this demo. But you notice, okay, it actually kind of worked. We're seeing things from 2016 and newer are at the top of the result set. In fact, I think I have to scroll down to like result 9 before I finally got one that was one that didn't satisfy that clause, but due to its frequency of the word burrito, it's still deemed a relevant enough result, right? So again, this is not a complete solution. I'm just painting a picture for you of how you can use boosting and these optional clauses to not get a complete custom scoring, but sort of influence the scores in ways to sort of have these positive effects. So I think that's a pretty useful technique. And like I said, this is a frequently asked question from end users. So that wraps up the demo section. I have a few more slides we're going to go back to. Many of you have probably seen our recent announcement about Couchbase Server 5.5 beta, which came out just a couple weeks ago. And the team I'm working on has had a lot of effort putting into improvements for this release. So I'm excited to talk about some of them here briefly at the end. The first is we have a geographical search and sort capability. Now this is not new. That was available as a developer preview before, but this is now fully supported. So we encourage you to use this. Some of you might be a little puzzled, like why would I do geo search in a full text? Why would I use full text for that, right? Again, the useful way to think about it is it's as a part of these supplemental clauses, right? So imagine someone is searching a data set for restaurants. you could find the perfect restaurant for them, but it's 1,000 miles away. It's not the one they're interested in, right? So you want to be able to additionally scope that down by some sort of geographic boundaries. And that would be like one of the first use cases, again, a bounding box search. You provide us the box, and we can then limit the results to that box. Or again, in a mobile use case, it's much more common. You know their location, or they tell you their location. And so now you can say, OK, I want a restaurant within 3 blocks. And you can scope it down that way as well. And finally, we do offer the ability to sort the results. Again, occasionally, you do want to just say, look, I just want the closest one first. And so we offer that sorting capability by geo points as well. The second major thing is we've added support for 11 new languages. We've gotten a lot of input from users that our language support was rather limited. We heard you, and we went back and added support. I have the list here. Briefly, Danish, German, Spanish, Finnish, Hungarian, Dutch, Norwegian, Romanian, Russian, Swedish, and Turkish all have some support inside of Couchbase now. So it's not complete. There's certainly others that we do want to add, and we want to hear from you about which were the other ones. What's missing that you want next? Please let us know, and we'll keep that in mind. But the bulk of the effort that our team has been working on was that users came to us and said, look, we love full-text search, but the indexes are just too big. Right? If I have a data set of, let's say, 10, 20 million, the index is 50 gigabytes, 100 gigabytes. It's too big. And so the ask for us was like, you got to go back and you got to fix this. So we put a lot of effort into a brand new index scheme. We built this from the ground up just to allow us to support larger data sets. And this is something internally we've called Schoch. It's going to be available as a developer preview in 5.5. So unfortunately, it's not going to be a fully supported feature in 5.5. That'll come in the subsequent release. But it was such a big deal. And when you see the numbers, I think you'll agree, we wanted to get it in your hands as soon as possible so we could hear back from you. So how does it work? Well, we got to go a little deeper into how the index actually works. And the best analogy is the index at the back of a book that you're all familiar with, right? It has a bunch of terms and page numbers. And that first set, like the terms on the left-hand side, in the full-text index, we call that the term dictionary. It's the list of all the terms that were in the documents that you indexed. What we've done is we have a brand new data structure to represent that term dictionary. This is something called a finite state transducer. It's a library we built called Vellum. It's actually open source. I should have mentioned that, so people are free to play around with that as well. But the main gain here is this compresses the data much better than before. If you remember from, if we just go back, right, those terms are in alphabetical order, right? So a lot of common prefixes are in the data when you look at it from top to bottom. And so that's one of the big ways that you get compression here. The second is, if I jump ahead, the second is that we get much faster fuzzy searching and regular expression searching. And the reason is this data structure has ways that we can sort of very efficiently perform those fuzzy searches on the data set. Previously, we had to scan the entire term dictionary to find fuzzy matches. Now we can much more efficiently do that. Now the second part, again, with that book analogy, is those page numbers, right? In the book, that tells you what page to go to find that term. In our index, that corresponds to the document numbers. That's how we know which documents used that term. And that's something we call postings list. And we're using a data structure called a roaring bitmap. This is, again, an open source library that's out there. And what this does, it lets us compress the document numbers into a very efficient form and lets us do much faster conjunction and disjunction. So anytime you have A, N, B, or C, like those queries, we can do a lot faster because these bitmaps can be sort of evaluated and consolidated much quicker. What's the bottom line for you? Well, I'll emphasize this is just one data point, but it's a really good one. I took the travel sample data set and I indexed it with the old index, and the index size was 859 megabytes. I took the same data set, the same index mapping with the new index, and it's just 234 megabytes. So this is, again, that's about 70% reduction. I don't want anyone to be misled to think all indexes are going to be 70% smaller. But between 50 and 70 is pretty common with the testing we've done. And so the bottom line for you is that means, again, twice the data can be indexed on the same hardware setup, right? And so it really does move the needle in terms of what types of data sets you can use the FTS support with. Because we're writing so much less data, the index build time is faster as well. So again, that was sort of a lesser goal, but also a nice one that came with having much smaller indexes to go with it. And finally, I would encourage you all to download this and try it. Like I said, this is available in the beta today. I know there are users who were reluctant to use FTS specifically because the size issue was something that had them concerned. So we would like you to try this again and let us know, where does this put us with your data set? Because we think this is a big change. So I thank you all for your time. And we do have time for a little bit of questions. We have a microphone, so I'd ask you raise your hand, wait for the microphone to come to you.
Here I come. I'm coming from behind. Oh, no, I get you this morning. I'll start over here.
What's the maximum Couchbase database size that you could apply full text search for? So we're evaluating a use case where we might have as much as 10 billion documents in a cluster.
So giving a hard upper limit is always difficult with Couchbase, mainly because of the scalability. We thought we had certain limits, and I was chatting with a customer yesterday, and they had gone 6 times where we thought the initial limit was, right? So depending on what you deem acceptable performance, it may work in some of those cases. Now, again, I'm not going to, 10 billion, I can tell you it probably does not do today. But the new index does move the needle. So we're, I think we're in the hundreds of millions now, but I don't know that we have not built a billion. We certainly have not done 10 billion yet. So I'd love to give you a more concrete answer, but we don't know what the actual limits are at this point. And I would say the thing to keep in mind is you also, when you say it's not just the size, can you build it? It's what are your perf requirements on the search with an index that size, right? Even if we could build it, if it took a minute to give you a search result, you'd say, well, that's no good. So I think we would want to know a little more about what your tolerance is there as well.
Okay, and then just one quick follow on. How much of the full text search performance is predicated on the full index being in memory versus part of it on disk?
Again, it does matter. We have stats. Again, I don't have a clean breakdown to say it's X faster when it's all in memory. It's faster when it does all fit into RAM. That much we know.
Okay. Thank you. I'll give you a chance now.
All right, thank you. So is Schoch also available for mobile side?
No, the full text search on the mobile is a little bit different implementation. So we've been working to sort of try and make the features comparable across both, but the underlying implementation is different on the server versus on the mobile. So.
Okay. Another question is about the date. Instead of a cutoff date, you can bump after that. Can you have a smooth thing like
Yeah, so as I said, this is not a perfect solution. It's a tool. But what I would say you could do is, so in real application, you wouldn't just hard code a date. It might be, let's say, the last week. So you've got some JavaScript which figures out what the date is, or maybe it's just client side, or you just know what the date is. You might say, okay, in the last week, I want to boost that the highest. But you're not limited to just one of those, right? You could say, maybe if it's in the last week, I bump it by 10. If it's in the last month, I bump it by 5. I don't know. So it wouldn't give you that perfectly smooth thing you're looking for, but you could do a decent job of approximating it. Like I said, it's not a perfect solution. Custom scoring is something we'd ultimately like to have, which would give you the ability to do that more perfect.
Oh, sounds smart. Thank you.
Thank you. All right, I got one back here.
Thank you. Is there a way to search based on paragraph or sentence scope, or something more narrow than just the document itself?
It would depend a little bit on how the things are structured in your document. So a good example would be, if you broke paragraphs up into, let's say, elements of an array as opposed to one thing, you could do some scoping at that level or break it up into fields. We have phrase search, which again allows you to find sort of a very narrow form of a proximity search. I want this within a certain proximity of this other. But not directly. I would say it would again be sort of like we could try and approximate it, but probably would want to better understand the use case and see there might be a better data modeling solution to it than just a hack solution in the search.
But I could look more into phrase search. You think? Is there documentation?
It would. Again, I think phrase could be related. I suspect phrase won't out of the box do exactly what you want either. So I'd need to know a little bit more, and you can certainly find me afterwards, and we can talk more.
Other questions? There we
There's
go.
one up front.
Always making me run up the room.
So I just want to understand this thing. I'm pretty sure with query we can do this, what I'm going to ask now, but I also want to understand if we can do this with search itself. I saw the plus for concatenation. Is there a way I can find items or where I don't want to see food at all, just the food?
Right.
So
we can, if time allows, I'll quickly see if we can do search. Oh, I don't know why I did that. So there's a, let's get rid of the date thing just to make this a little simpler. So this is like must have burrito, but we could do minus food. And that would say like must not have food, the word food in this. And again, it could be a type field. If you had like, if you knew all the food documents were a certain type, you could just do it on a type field too. So.
Is there a limit of how many plus you can use it?
No, it's it could. So the question was there a limit on how many terms, like pluses or minuses? Yeah. There isn't a hard limit. Again, the complexity of the query is going up. You're asking it to do more. In fact, the more pluses, actually, the faster the query can get. And the reason is those are like requirements. It must have this. So what you think about it, you're actually down selecting the number of documents that could possibly match when you add another plus. So that's a sort of a hidden secret. It's a little counterintuitive. The more plus things, the more musts you have, actually, that can improve the query performance.
Well,
one more. Oh,
all right,
sorry.
one more. All right.
Explain. I'm sorry.
You're going to get.
You said with more plus, it will be faster or efficient. I just want to understand that.
You're right. So I could say it would both. I guess both, but like faster is sort of a bit relative here, right? So faster. What I mean by faster is when you say food. Let's say you just said food by itself. We have to essentially look through all the documents that used food. Mm-hmm. But when you have plus burrito, I can skip over a bunch of the documents in like the way the postings list is organized for food. I can jump ahead if I know like. The first document that uses burrito is document 1000. I can skip over document 0 through 99 in the food list. So it does make it faster to navigate through the food posting list because I'm able to skip over things that I know didn't satisfy the burrito part.
But if they're all plus, I'm sorry, if they're all plus, right, and we have more than 10, say, will the search be slower then? Because then it has to scan.
What I haven't done is I haven't done a test to say, I'm going to do 1 and then 2 and then 3 and see if it gets faster. I just know the implementation is one where by having plus, you're reducing the amount of work for those other queries. The reason people don't just put plus in everything is that's ultimately not what users want, right? With search, they have a bag of words. It has to match some of these, but not all of them. And when you put plus in front of everything, it just ends up not matching what the user expects.
Marty, thank you. I think that was a great presentation.
Okay.
Really appreciate it. Give him a hand. And thank you, everybody, for being here. We'll start the next session in about 3 minutes. Thank you.